For the rest of the semester, we'll be guided by questions such as the following. Can we effectively decide whether a sentence is provable from a theory? Can we effectively decide whether a formula is a validity? Or can we effectively decide whether a sentence holds in a given structure? Of course, this depends to a large extent on what we mean by effectively decide. And since we want to treat these questions as rigorous mathematical questions, so what we need is a mathematically rigorous definition of decidability or effective decidability. Later, we also have to worry about then what does it mean to represent a theory with respect to decidability questions or represent a structure and so on. Well, there are several or numerous possibilities to define the notion of effective and computable and decidable in a rigorous way. It turned out that all these notions led to the same concept. Namely, they were all equivalent to the concept we're going to study in this lecture, namely Turing computability. So we'll get back to this kind of question of the equivalence of notions of computability a little bit later. Turing computability is based on the notion of a Turing machine, and it is an abstract model of a machine computation as we know it today, as a computer operates today. So if you know a little bit about architectures of computers, you'll maybe recognize some of the elements there. They're very simple and also very abstract, but Turing's original idea was to kind of model a human doing computations on a piece of paper. At the time when he defined it, there were no computers in existence, such as the powerful machines we know today. So it seems all the more remarkable that he envisioned, while trying to come up with a rigorous notion, a mathematical definition of computation and computability, he envisioned an architecture that seemed so universal that it is in many ways replicated in any computer that we use these days. So the basic components of a Turing machine are the following. We have a tape here that's called the working tape. It is a bi-infinite tape in our treatment. There are other ways to define it, but they all lead to the same notion of computability. I'll mention a few of them, a few variants later on. So we have a bi-infinite tape. The tape is divided into cells, and the cells can hold symbols, and these symbols can, for us, either be a B, which means a blank symbol, or a symbol 1. Furthermore, it should be stressed that at any point of a computation, only finitely many symbols on the tape are non-blanks. So there's at most finitely many ones on the tape at any time of a computation of a Turing machine. Now the tape can be monitored and altered and edited using a read-write head that always points to a single cell. And this read-write head can read the current cell, it can change the content of the current cell, and it can move. Right? And all this happens according to a program. So a program that controls the movement and the editing process of this head here. And a program is what you would expect, just a finite list of instructions. And what those instructions look like, we will look at next. To formally specify an instruction, so a line in a Turing program, we need two sets. One is the set Q, that is the set of states. It's a finite set, and two of those states are special. There's state Q0, which is called the final state, and Q1, which is called the initial state. So the idea is that at any time of the computation, the Turing machine is in a certain state. It always starts in state Q1, and as soon as the computation reaches or gets into state Q0, that means or signals to the machine that the computation has ended and it's time to output something. Next, we have the symbol set. So in our case, since we only allow two kinds of symbols, that's a very simple set, namely just one and the blank symbol. There are other possibilities here, but the important thing is everything is finite, right? So this is a finite set, this is a finite set. Then finally, and this is the important function in terms of controlling the read-write head, there is a transition function. This transition function is traditionally denoted by delta. And what delta does is that it is a function from pairs of a state and a current symbol. So think of it, that's the current state that the machine is in, and that's the symbol that is currently read by the head. Okay. And then depending on that, what state it currently is in and what it currently reads, it passes to a new configuration that is determined by a new state, a new symbol. So that would mean it would overwrite the current symbol by this new symbol and then moves either left or right. There's also variants possible here, like we also have like stay in place possibility here for movement, right? So, but again, these are all equivalent when it comes to what kind of functions we can compute. Okay. So an important thing is that it is not necessary that delta is defined on any possible configuration, right? So we might have a configuration or an input here Q, a pair QS, for which this function is not defined. In that case, as we will see in the next slide, we'll say that the machine just stalls, right? So in this case stalls, and in particular it does not produce an output in that case. So what does a Turing computation now look like? As I already said, the Turing machine M always starts in state Q1. The input, the initial input, is a natural number, x, so this is in n. And this input, since we only have ones as symbols, non-blank symbols, we represent this natural number just by x plus 1 many ones. X plus 1 because we also need to represent 0. So if we have a number, we write, just give the x plus 1 many ones on the tape, and the head is placed on the leftmost one. Okay. So this is how the machine starts. And then a computation step says, okay, we look at the current pair of what state I am in, or the machine is in, and what symbol is currently read by the read-write head. We find the value of the transition function for this pair here. As I already said, if this is not defined, then M stalls, and this up arrow just means that in this case, the computation is not defined, or M does not halt. And this is represented usually by an upward arrow to indicate that the machine does not halt on this input. So if, however, it is defined, and let's say it's Q prime S prime X, we write S prime on the current cell. We move the head one cell in the direction of X, so left or right, and enter state Q prime, and then repeat the whole thing again. That's what one computation step would look like. So how does a computation of a given Turing machine terminate? Well, if the computation ever reaches state Q0, remember that was our halting or final state, In this case, we say the computation halts. We also write m of x down arrow. Right? And the output will just be the number of ones on the tape. Remember, there are only ever finitely many at any time. There are only finitely many ones on the tape. That number of ones is the output of the computation on input x. If it never reaches Q0, or if it stalls, right, means at some point we can't find a valid transition, or the transition function is not defined, then we do not halt and the output is not defined. So in this case, we write mx up arrow. So let's do a simple example, and I think that should illustrate rather intuitively how a Turing machine works. So we write the transition function here as quintuples, meaning it's this is the input, and that would be the output of the transition function, right? Or the value of the transition function for this pair here. We here we have our program, right? Here we have our input, x equals 2. That means it will be represented by 3 ones. We start always in state Q1, and the read-write head is originally positioned over the leftmost one. Okay. So now we check, we start the computation. We are in state Q1. We read currently a 1. We look up an instruction. Oh yeah, here is an instruction with that starting pair. Well, it tells us to go into Q1, write a 1, and go move the read-write head 1 space to the right. So here we did that. Right. So we moved 1 space to the right. We wrote the 1. There was already 1 there, so there's no change in the cell content, and we're still in state Q1. Now we see, yes, we're still in the same combination here, content, state, so we do exactly the same thing once again. And so we did that. We moved to the right, and we are still in state Q1, and we see still nothing has changed. We're still in state Q1. We still read 1, so this line of our program still applies. So we do this one more time. So now we're moved 1 to the right, and we're still in Q1. But now we see, oh yeah, that line does not apply anymore. But we see now, here there's a line Q1 blank. I apologize, here's a capital B. I use little b's here. That's of course meant to denote in both cases the blank symbol. All right, so we're in state Q1. We read a B. Well, what does the program want us to do? We go into state Q2, write a 1, and go to R. So let's do that. So we executed the command, right? We wrote a 1 here, went into state Q2, and moved to the right. So let's see, we're in Q2, we have a blank symbol, so this line applies now, here. It wants us to write a 1, go 1 to the right, and go into the final state. So we did that. We wrote a 1, moved to the right, and entered state Q0. But now we see we're in the final state. So now by the rule, the output rule, we just output the number of ones on the working tape. So in this case, our output would be 5. And as you can see, so what happens with this program, if you analyze it a little bit more, you will easily see that, well, the program just goes over cell by cell, always, as long as it reads once, it goes to the right. Once it reaches a blank, it writes another 1, and then it goes to the right, writes another 1, and then it stops. So essentially what it does is it adds 2 more 1s to the input. So it will in this case, always output the number that is by 3 larger because of the imbalance, right? So here we always add 1 to the input, so we represent 2 by 3 ones. So in order to output 5, we only need to add 2 ones. So, but in general, this program would, on input x, always output x plus 3. And this brings us now to the function that is computed by a Turing machine, namely a function f from x to n, where x is a subset of n. So we have to look at so-called partial functions now. These functions f are not defined necessarily on every natural number because we always have the possibility that our machine does not halt. That's why we consider partial functions, right? So such a function is called partial Turing computable if there exists a Turing machine that on input n, if n is in x, it halts on input n and outputs f of n. But if fn is not in x, m does not halt in input n. So it either goes in, either never reaches the, it goes in an infinite loop, or it just stalls because it cannot find a transition, a valid transition. So it goes in. If it's in x, it halts and outputs f of n. If not, then it goes in an infinite loop or stalls. As I already mentioned throughout the lecture, there are several variants on the Turing machine concept that you can find in the literature. They all lead to the same notion of a Turing computable function. So one thing is you can allow multiple inputs in the sense that you want to, for instance, compute functions that are defined on x0, x1 to n, or so where the xi are subsets of n now, or even more higher dimensional functions. So this is, you can make possible by just writing these inputs on the tape, separated by blanks. You can also, or you could, for instance, decide you work with multiple tapes instead. That's also possible to define this. You can work with one-sided tapes instead of bi-infinite tapes, as we worked with here. You could also enlarge the tape alphabet as long as it stays finite to allow, for example, binary inputs, right, or representation of numbers as binary. That's all possible. You could also change the format of the instructions. So there's various ways how to write them, but the basic concept, underlying concept, always remains the same. And consequently, they all lead to the same notion of a partial Turing computable function, as one can prove. So the important thing is that the concept that we define here is mathematically rigorous, and it is also the notion of a Turing computable function or partial Turing computable function is invariant under these possible variations of the concept here. We will not prove these equivalences or address these variants any more or much more in the rest of the course. So just you have to take my word for it that these indeed all lead to equivalent concepts of computability. So what we'll do next is we will analyze this notion of a partial Turing computable function a little bit more and prove some important results, such as the existence of a universal machine and so on.